Does your smartphone have more compute power than mankind had at its availability to land on the moon? That sounds absurd, but can it be true? And more importantly, does this comparison at all make sense? Let's find out. Some time ago, I watched a movie about a cruise ship. I remember a little boy reading out, "This ship has more horsepower than Napoleon had to conquer all of Europe." I was intrigued. That sounds impressive, but it's also kind of nonsense. Of course, if all horses pulled the same rope, the ship would win against them. But for Napoleon, 1,000 horses didn't mean raw power, it meant logistics. Every horse had to be fed, watered, cleaned, cared for. It needed a soldier. Horses were not engines, they were living supply chains. A horse could win a battle, a ship cannot. So comparing the ship's horsepower to Napoleon's cavalry is more marketing than engineering. And exactly the same mistake happens when we compare a modern smartphone with the Apollo guidance computer. I've done professional benchmarking for more than 10 years, working with companies like Dell and SAP. And there's one thing I have learned. You must optimize for the task at hand. Numbers alone are meaningless. Take frequency. My phone runs at 3.1 gigahertz. That means 3.1 billion operations per second. Sounds insane. But what kind of operations? To understand this, we need to go all the way down to machine language. I have made a video about the difference between machine language and assembler, but I will just use these two terms synonymously here. So, one instruction available today and already available on the Apollo computer is the add instruction. Add add one register into another one. That's it. Subtraction, multiplication, division. Enough to calculate a trajectory in a few thousand lines of code. That's all Apollo needed. And what happens when I try to execute this nowadays? Nowadays, it does not even let me execute this program because it is not secure in a multi-user, multitasking system environment. Apollo computer didn't have to care for this. It just did what it was instructed to do. Here we have all these layers of security against hackers, against multi-users, against multitasking programs interfering with each other. All this was not needed with the Apollo computer. And look what we stack on top today. We have silicon. Out of this, we build transistors. Out of those, we build logic gates, adders, assembler, machine language, then a Linux kernel, C runtime environment, standard library, terminal emulator, font rendering, Windows system, a GPU pipeline, and all this just to print "Hello World." These days, 1969, it was probably enough to have some adders, and the people would solder them together and wouldn't even need assembler or machine language, maybe from time to time. But after all, they knew what they were doing. They were, after all, rocket scientists. By the way, if you want to compare two computers nowadays, for example, you want to know if a Raspberry Pi is faster than your notebook, or if you can dare to replace your notebook by a Raspberry Pi, or when you know how much virtualization overhead you get in a virtual machine, then I recommend you to do this. But first of all, this is not valid for floating point operations, and it is not valid for disk I/O or network I/O. It is just for the compute power, just for the cooperation between CPU and RAM. I recommend you to do a df-h, then you see where the shared memory is. Then you run a quick test where you just output as many 0 bytes as possible into a file in your memory. And then you see how quick and how fast this computer is. In this case, we see 1.7 gigabyte per second. So it is writing more than 1 million bytes per second. And then you need to repeat this test because it vastly fluctuates. So let's do it again. Now we have 4.5 gigabyte. Let's do it again. And it's coming to a plateau. So this computer here is virtualized, by the way, and it writes about 4.5 billion bytes per second if you tell it to write as quickly as it can into memory. So this is how I compare the compute power of computers in a quick fashion. But let's go back to Apollo. So my mobile phone has 8 CPU cores, and it has about 3 gigahertz per core. It has 16 gigabyte RAM, and that gives it a performance of about 100,000 million instructions per second. So 100 billion instructions per second. A GPU has trillions of operations per second, but I want to be generous towards the Apollo program. So when we compare this, we look at the clock speed. Apollo had about 1 megahertz. The smartphone has 24 gigahertz. If you regard that we have 8 cores, 4 kilobyte versus 16 million kilobyte. And when you look at the performance, Apollo could perform less than a million. No, my mobile phone can perform more than a million as many instructions per second than Apollo could. So in all regards that matter, RAM and performance, my mobile phone is more than a million times faster than Apollo. There were roughly about maximum, really generously, 100,000 computers in the world 1969. So the answer is yes, this thing here has more compute power than humankind had at its availability to fly to the moon. And this is something that really bogs my mind every time I think about it. Now, my favorite video about the moon landing does not prove that we landed on the moon in 1969. It shows that it was impossible to fake it these days. And that's really cool insight, because faking it would have required 3D graphics, lighting, shadows, perspective, camera motion. You must render every single pixel many times per second. That requires massive graphical compute power. Today, with gigantic GPUs, it is easy to render realistic scenes. In 1969, there was nothing, not even close, which means it used to be easier to fly to the moon than to fake the video of it. Because computers that create videos must more be like your smartphone and not like Apollo's guidance computer. So when someone claims the moon landing was fake, they overestimate the compute power of 1969 and underestimate engineering. Apollo wasn't a triumph of hardware. It was a triumph of engineering discipline, focus, and simplicity. And maybe that's the real lesson. It's not about how powerful our computers are, but how carefully we choose what they should do.